Okay, types of solutions. You can make a solution from any combination of phases. By phase, we mean physical states of matter, solid, liquid, gas. When we talk about an aqueous solution, the solvent is water. The solute could be a gas, a liquid, or a solid. And so here we have examples of different types of solutions. Air is a solution, mixture of gases. Club soda is carbon dioxide and water, so a gas dissolved in a liquid. Vodka is ethanol and water, a liquid dissolved in a liquid. And seawater is a solid dissolved in a liquid. You can also have solid solutions, two solids dissolved in each other. We call these alloys, if it's metals. Brass is an example of a solid mixture, a mixture of copper and zinc. Now you can't take copper and zinc and just like put them next to each other and have them mix. You have to heat them up, melt them, and then they'll mix, and then you cool them down and you have a uniform mixture. You've got a lot of difficult questions. Would you have to heat them to the same temperature or just to their melting points? You'd need to get both of them melted. So you'd have to heat them to the melting point of the one with the highest melting point, I believe. Yeah. Any other questions? I like hard questions. It's interesting. So a particular solvent will not dissolve all possible solutes. This is a really good thing, because if everything dissolved in water, what would the Earth look like? It would just be, I don't know, this big puddle. Drop. Yeah, it'd be a giant puddle, basically. We'd dissolve in it, everything would dissolve. So some things dissolve in water, some things don't. And then there's also a limit to how much will dissolve. So solubility is the amount of a substance that will dissolve in a given amount of solvent. So this can be expressed in many different ways. It's often expressed in how many grams of the solute will dissolve in like 100 grams of the solvent. It could be any quantities, but you have to specify amount of solute and amount of solvent. The solubility depends on that natural tendency towards mixing and also on the types of intermolecular forces that are present. So many physical systems tend towards lower potential energy. Lowering energy drives many of the processes. When you form a solution, it doesn't necessarily lower the energy. So if we look at a container with neon gas in one compartment and argon gas in the other compartment, and we've got a barrier here, and we remove the barrier, what's going to happen? They're going to mix. Because we learned about what gases do, and gases travel in straight lines. The particles travel in a straight line till they hit something, and then they bounce off. And so you remove this barrier, and these bouncing balls are going to get all mixed up with each other. Does that lower their energy? It actually doesn't really change their energy at all. They're mixed together, but they still have the same energy that they had before. So mixing two ideal gases doesn't lower their potential energy. So why do they mix? What is causing them? There has to be some force that's causing them to mix. It's entropy. One way to define entropy is a measure of energy randomization or energy dispersal in a system. The idea that energy tends to spread out. So when those two gases mix, the kinetic energy of each gas becomes spread out over a larger volume. That increases the entropy, and that is a spontaneous process. So substances mix due to the pervasive tendency for energy to spread out whenever it is not restrained from doing so.
So they just want to take up more space?
It's not that they want to take up more space. They're just spreading out. So their energy, the energy, they have kinetic energy because they're moving, right? When they are confined to half of this container, their energy is within that container. When they spread out, their energy is spread out. Entropy also explains transfer of thermal energy. We talked about the fact that this occurs. Thermal energy is transferred from warmer objects to colder objects. We didn't go into why does that happen. It happens because of entropy, this tendency towards dispersing the energy. So you've got hot coffee and a cold ice cube. The energy from the hot coffee is transferred to the cold ice cube to spread out the energy, to disperse it more.
So it just always wants to release energy?
Energy wants to spread out. Yep. And we see effects of entropy in many everyday occurrences. Another way to think of entropy is that it is a measure of the disorder of a system. So right now it's fall and the leaves are falling from the trees, right? When the leaves are on the trees, they are ordered, right? There are patterns to how the leaves are attached to the branches and the twigs. When they fall, do they fall into neat piles or patterns on the ground? No, they're all over the place, very disordered. Their entropy is increased. If you play 52-card pickup, you take a deck of playing cards and you flip them and they go all over the place, right? Can you take those and throw them up in the air and have them go back into a pile? No, because that would be negative entropy change, and that's not a spontaneous process.
Can you get negative entropy? Yeah.
Well, you can have something that has a negative entropy change, but it requires another form of energy to put in. So can you take those messed up playing cards and put them into a deck? Yeah, you can, but it requires you to pick them up and put them in the deck, right? It's not going to happen by itself. If you just give them a toss in the air, they will spread out all over the place by themselves. They're not going to just stay together and land.
So positive entropy change?
That would be positive entropy change, yes. They're spreading out. Entropy has increased. There's increased disorder. There's increased energy dispersal. When you put them into a pile, then you are decreasing disorder, so that would be a negative entropy change. My house is a testament to entropy, right? Unless I put significant effort into it, it gets really messy really fast. My house bears some striking resemblances to a frat house, unfortunately. But, that's what happens when you've got 6 boys. Because the husband, is male also. Okay. Very tangential today. So how do intermolecular forces affect the formation of a solution? They can promote the formation or they can prevent the formation. So if we have similar types of intermolecular forces, that can promote the formation of a solution. If the intermolecular forces that the solute and the solvent have are very different, that can prevent the formation of a solution. So if we have 2 substances that both have dispersion forces, they will most likely form a solution. Here we have example of 2 substances with dipole-dipole attractions. So they're going to form a solution most likely. You can think of the different types of intermolecular forces as the language that these things speak. If 2 groups of people have a language in common, then they're much more likely to mingle and mix and talk to each other, right? Whereas if you have those same 2 groups of people and they only speak different languages, they're not going to talk to each other because it's just hard. You're going to talk to the people who speak your own language. So that's kind of what it's like with the particles here. Hydrogen bonding, ethanol and water, they have the same language. They have the same type and strength of attraction, the hydrogen bonds. And then the ion-dipole force, this is between ions and the dipoles, generally in water. So we have forces, intermolecular forces, between the solvent particles. We have intermolecular forces between the solute particles. And then we also have intermolecular forces between the solute and the solvent. So let's pretend that this is, let's say, sugar, and this is water. there are forces of attraction between the water molecules, the strongest being hydrogen bonds. There are also forces of attraction between the sugar molecules. Those also have hydrogen bonds. So between water and sugar, they both have hydrogen bonds, and so they will form a solution. We have this saying, like dissolves like. If the solute and the solvent are similar intermolecular forces, a solution will probably form. Probably. It's a little more complicated than that. And I think we used this word earlier, miscible. Miscible means that you have two liquids that are soluble in each other in all proportions. Meaning you could have a small amount of one or a small amount of the other, and they'll still mix freely. Not all liquids are miscible. So, excuse me. Whether the solution forms or not depends on the relative strength of the interactions. So if we've got solvent-solute interactions, and those are strong compared to the interactions of the solvent with itself and the solute with itself, the solution is likely to form. If they're roughly the same, a solution will form. But if the solvent-solute interactions are weaker than the interactions between the solvent with itself and the solute with itself, it's going to depend on the relative disparity. If these interactions are very, very weak compared to this, the solution's not going to form. When the solution forms, you have a gain in entropy, but in order to form the solution, you have to break the interactions between the solute molecules and between the solvent molecules, and that requires energy. And so you have a balancing act here of increasing energy and decreasing entropy. Okay, determine whether each compound is soluble in hexane. What do we look at to determine whether things are soluble or not? A solubility table. We could look at that. The solubility table, though, that we used in the earlier chapter had to do with ionic compounds in water. So it's not going to help you with this one dissolving in hexane. But for ionic compounds, that's exactly what you would do. How do we determine whether two things are going to dissolve?
Look at hexane molecular structure.
Yeah, we're going to have to look at the molecular structure and specifically at the types of intermolecular forces. So like dissolves like. So hexane, is this polar or nonpolar? It's nonpolar. First of all, you have to remember what hexane is, right? We did learn the alkanes. Hex means 6, and hexane is just 6 carbons with hydrogens. So even if you don't know the exact formula, you know it's carbons and hydrogens. So it's C6, and if you draw it out, you'll find out it's 14 hydrogens. Carbon-hydrogen bonds are nonpolar. Carbons don't have lone pairs. Anything that is just carbon and hydrogen will be nonpolar. So this is going to have what types of intermolecular forces? Dispersion forces. So this has dispersion forces as its strongest intermolecular force. Well, what about water? Polar or nonpolar? It's polar. And what type of intermolecular forces does it have? The strongest one. Hydrogen bonding. So water has hydrogen bonding. Is hydrogen bonding like dispersion forces? Are they the same? No. So will water dissolve in hexane? No. They are not alike. They don't speak the same language. They don't have the same type of intermolecular force. So the answer here is no, not soluble. How about ammonia? Pardon me? Hydrogen bonding. So, we talk about ammonia a lot, so you might remember that. If you don't, you should be able to fairly quickly draw a Lewis structure for ammonia. And we see that nitrogen has a lone pair. Anytime you see a lone pair in there, it's probably polar. And then we learned about ET phone home. Here we've got the nitrogen-hydrogen bond. And so this is polar, and it has hydrogen bonding. So this is also hydrogen bonding. Is that going to dissolve in hexane? No. Would it dissolve in water? Yeah, probably would, because they both speak hydrogen bonding. How about propane? What's propane got going on? Dispersion forces. It's just carbons and hydrogens like the hexane. So it's nonpolar and it's got dispersion forces. Is that going to dissolve in hexane? Yeah. Because it's like hexane. How about hydrogen chloride? Is that polar or nonpolar? It's polar. So we're not going to do anything on exams where we have to look at a table of electronegativities and actually find the difference in electronegativity. We need to have just more of a general knowledge. And so if the two elements are different, I want you to assume that that's going to be a polar bond. That is not always true. But it's true most of the time, and most of the time is good enough for Chem 1A. The only exception is these carbon-hydrogen bonds. Those are nonpolar. So we look at this as two different elements. We say that's probably polar. So this is polar. Does it have hydrogen bonding? No. It's got a hydrogen in it, and the hydrogen's bonded to chlorine, but that's not what hydrogen bonding is. You have to have fluorine, oxygen, or nitrogen. So what kind of forces does this one have? Dipole-dipole? Because it's polar, it has a permanent dipole, and dipole-dipole forces are stronger than dispersion forces. So this is polar. Is this going to dissolve in nonpolar hexane? No. So these are this sort of question is something that could show up on the exam. Any questions about that?